Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters for making this video possible, and we'd also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Seba, and today we're going to investigate a quite simple and intuitive, yet very relevant and useful technique in statistics, that is the Spearman rank correlation coefficient and the test for its statistical significance. The motivation for using the Spearman rank correlation coefficient instead of the more popular and widely used Pearson correlation coefficient, widely known as just the correlation coefficient, are outliers in the data and the non-normality of many variables that you will investigate and try to identify correlation between them. And just for a motivation, just for an example, we are investigating the dependence between economic growth, the GDP per capita growth in 2019, with the initial GDP per capita, that is the natural logarithm of GDP per capita across 131 countries. Here we will test for convergence, that is, whether poorer countries grow faster and are catching up with their richer counterparts, which is a quite common, a quite famous theory in economic development and economic growth overall. And the problem is that if we visualize our data using a scatter plot, using log GDP per capita on the x-axis and the GDP per capita growth on the y-axis, we can see some outliers that can skew the picture and influence the calculations of the standard Pearson correlation coefficient. And if we calculate the standard conventional Pearson correlation coefficient using the Corral function, inputting the two array in question, that is the initial log GDP per capita and the GDP growth per capita over here, we can see that the correlation is indeed negative at minus 0.13 approximately, but it can be impacted by the outliers over there. To mitigate the impact of outliers and non-normality, we can use the ranks of those variables and calculate the Spearman rank correlation coefficient using this particular formula. This formula utilizes the sample size n over here that we can determine using the count function, counting any of our variable arrays that we want, and we can verify that we've got 131 observations indeed. And we need to also consider the differences between the ranks of observations for the particular country and square them, and then calculate the sum of such squares, and that would constitute the formula. Quite intuitively, if the difference between the ranks is quite small, this component would be quite small as well, and if we subtract it from 1, we'll get a Spearman correlation coefficient of quite close to positive 1, meaning we'll get a correlation coefficient that identifies tight positive relationship between the variables. If, on the other hand, the differences between ranks are quite massive, quite material, then this correlation coefficient can get as negative as minus 1, signifying the negative relationship between the variables. To get over with our Spearman correlation coefficient calculations, we need to input the ranks of our observations, so just rank them. And here, the rank function is quite useful. We can refer to a particular observation, either log GDP per capita or GDP growth. Then we need to input the array that we are concerned with. So here we can just lock the rows, and then we can specify in which order do we want to rank the variables. 0 for descending order and 1 for ascending order. Here it doesn't really matter what you pick as long as you are consistent for both of your variables. So let's pick the descending order here, inputting 0. And we can see that Algeria is the 83rd richest country in our sample. It means that it's below the median in terms of initial GDP per capita. And if we drag it across, we can see that GDP per capita growth in Algeria is 114th highest in the sample. And we can see that's quite low, as we've got 131 countries. And Algeria's GDP per capita actually declined in 2019, and that is verified by this rank being quite high, meaning it's quite close to the bottom, quite close to 131. And if we bottom right click it all the way down, we can calculate the ranks for both variables for all of our sample countries. For example, we can see some evidence of the convergence hypothesis being true, of the inverse relationship being prominent in the data set. For example, Bangladesh is quite a poor country in terms of log GDP per capita, but it's growing quite fast, catching up with its richer counterparts, with GDP per capita growth being higher than 7% per annum, which is the third highest in the whole sample. Some countries are in the middle. For example, in Belarus, both the log GDP per capita and GDP per capita growth are the 69th highest in the sample, which is quite nice. And we can see other evidence that something like that is happening. However, to rigorously test the convergent hypothesis using Spearman rank correlation coefficients, we can calculate the differences in terms of ranks. So just subtracting the GDP per capita growth rank from the log GDP per capita rank, it doesn't really matter which way or the other you subtract, simply because the ranks difference is going to be squared for the formula. And as long as it's consistent throughout, we will be fine. So we bottom click this formula all the way down and see the differences in terms of ranks. And if those differences are massive, then our Spearman correlation coefficient will turn out negative. So now let's calculate that. Let's just subtract from 1 6 times the sum squared of rank differences. And to adjust it, we can divide it by n, which is the sample size, times n squared minus 1. And that will normalize our correlation coefficient to be bounded from -1 to 1. So it can be interpreted the same way as we interpret the simple Pearson correlation coefficient and compare the two as well as their statistical significance. And we can see that the Spearman rank correlation, computed using this formula over here that we have just translated into the language of Excel, is quite higher in magnitude than the Pearson correlation coefficient, as it mitigates the impact of outliers and non-normality, and is equal to minus 0.18, which is quite a bit higher. Now, to test for significance, we can use a very simple heuristic that you can calculate. You can convert your correlation coefficient rho into a t-stat with the degrees of freedom n-2, n being the sample size, using this formula over here. And it's quite simple to understand that if your correlation coefficient is quite low in magnitude, then the t-stat will be quite low and insignificant. And if the correlation coefficient is quite large, then the absolute value of the t-statistic will increase and could perhaps exceed the relevant critical threshold. And also it does depend on the sample size. The higher the sample size, the more significant your correlation coefficient would be, as there is less chance that this is just happening due to some random fluctuations in the data and the result is genuine. So to calculate the t-stats, we can just input this particular formula. So we'll multiply our correlation coefficients, so both the Pearson and the Spearman rank correlations, onto the square root of, in the numerator, we have got our sample size. We can log the row over here, as the sample size is the same for both coefficients, minus 2, and we divide it by 1 minus the respective correlation coefficient squared. And we can see that the t-stat for the Pearson correlation coefficient is minus 1.55, and the t-stat for the Spearman correlation coefficient, as we drag it down, is equal to 2.08. And we can see that the Spearman correlation coefficient gives you a higher value in that case, reflecting the fact that this particular t-stat was quite a bit lower, as the normality assumption was not fulfilled and as the outliers are influencing the results. And now we can use our usual two-tailed t-distribution, our two-tailed t-test, to convert those into p-values and compare with a desired critical interval. So we can input t-dist two-tailed, input the absolute value of our t-stat, and minding this particular formula, we can input n-2 again as the number of the degrees of freedom for our two-tailed t-test. And we can see that the p-value for the Pearson correlation coefficient t-statistic is 12%, which is higher than the 10% confidence interval, meaning that this relationship is not significant enough. And as we repeat this procedure for the Spearman correlation coefficient t-statistic, we get a p-value of approximately 4%, which is lower than 10% and even lower than 5%, meaning that the convergence hypothesis, the negative relationship between log GDP per capita and GDP per capita growth is maintained at 5% significance, meaning that as we use a more robust to non-normality and outliers procedure, which is the rank correlation, we can identify the result that we seek with greater precision. And that's all there is for the Spearman rank correlation coefficient, its significance testing, and comparison with the conventional Pearson correlation coefficients. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.